This is a short section to take a look at power and how power is related to electrical energy, voltage, current, and resistance. First of all, if we refresh our memory about power, power is the rate at which work is done. And electric power is the rate at which charge carriers do work. The charge carriers convert electrical potential energy into non-electrical forms of energy. So again, our definition of power is change in energy over time, or also work over time. And our change in energy is in our change in electrical potential energy over time. From last unit, we remembered that our definition of voltage, or our change in voltage, is the change in electrical potential energy over charge. So we can also say that change in electrical potential energy is equal to change in voltage times charge. So for electrical power, if we put those together, we can say that charge times change in voltage, which is our electrical potential energy, divided by change in time, is our equation for power. Charge over time is current. So current times change in voltage is a way to determine electrical power. All right, we have power is equal to current times voltage, and Ohm's law is voltage equals current times resistance. If we combine these two equations, there are actually a couple of different ways that we can write the power equation. So the first way would be to substitute current times resistance for voltage. So we have power equals current times resistance, so we have power equals I squared R. We can rewrite Ohm's law so that we have current equals voltage over resistance. If we use that now and put that into our power equation for current, we have power equals voltage over resistance times voltage. So now we have V squared over R. So there's another way that we can write power. This tends to be the way that we look at dissipated power in conductors. If we take a look at this next exercise, we're trying to find the current going through a 100-watt light bulb. And this is a light bulb in your house, so we're going to deal with household voltages. Remember, that's some value that you should remember. And we want to find the resistance of the light bulb. First thing we need to do, it says, is find the current. So we know power is 100 watts. Voltage is 120 volts. We want to find current. So we're going to use our first definition, our first equation for power. Power equals current times voltage. So current is going to equal 100 watts divided by 120 volts. We get 0.83 amps. The next part of the problem asks us to find the resistance of the light bulb. So we now have enough information that we could do that with Ohm's law, or we can go back to our original data and use a different power equation. We know voltage, we know power, so let's use a voltage, power, and resistance equation. So power equals V squared over R. So we have 100 watts again equals 120 volts. Square that over the resistance. So through the magic of algebra, what we find as the resistance of our light bulb is 144 ohms. And so that is working through and looking at the relationship between power, voltage, current, and resistance. Now we're ready to start building circuits and looking at voltage, current, resistance in multiple resistor circuits.